Alright, we're going to be going over this electricity and magnetism big quiz. So those of you who are making use of this, you're going to be really prepared. First question, true or false? Current passing through a conductor is increased from 10 amps to 15 amps. This decreases the strength of the magnetic field produced by the conductor. Well, this right here is a resounding false. And the reason it's false, come on, give me the right with you. The reason this is false, alright, is we know that the more current, according to what we learned about magnetism, is the more current flowing through there is going to increase, alright, that magnetic field. Alright, this will increase the strength of the magnetic field. Alright, the next one I want to go over here then. Number 2. The strength of a magnetic field is measured in Teslas. Well, yes, because the magnetic field is measured in, we call it Bill. If you remember, we have our equation, F equals I times L times B, Fib, or some people have just started remembering force equals Bill. B is what we measure the magnetic field in, and it is in Teslas. In your guys' lab, most of you got something close to 0.48 milli Teslas, and you guys had to convert that to 0.00048 Teslas to be able to use that equation. All right, number 3. The force on a current carrying wire in a magnetic field is proportional to the current flow of the length of the wire in the field and the field strength. So, we've got this wire. Actually, okay, we're going to create some magnetic field here. That's B. And we've got this wire that's running through here. So this is our L. And we're going to say that I is the current that's flowing through this wire. Well, this is true. It's proportional because the force, if you think back to our equation we just said, is proportional to the current. If I increase the current, the force goes up. If I increase the length of the wire, right, that's running through this field, the force is going to go up. Or if we were to put more magnets down here, and increase the amount of magnetic flux, magnetic field, then we're also going to get more force by doing any one of those. Okay, a magnetic field exists around any current carrying wire. Well, this goes right back to the first right-hand rule. Alright, if I have a wire, alright, here's my wire, and we know that due to the conventional current is the flow of protons, we know that the right-hand rule tells us that if you take your thumb and put it on here in the direction that this is going, so I'll take my thumb and then wrap my right hand around here so that my fingers would be coming out around this side. Draw some really bad looking fingers here, and it's also going to be a cartoon fingers because I'm only going to have 3 fingers here to go with this as well. Alright, so there's my hand. You find out that the current is traveling in the direction of your hand. The current goes like this, alright, and that's the right hand rule. If there's current flowing through the wire, there is magnetic field. Okay, magnetic field exists from north poles of magnets and enters the south pole of magnets. That's 100% true. If you think about the Earth, I'm going to draw the Earth up here in green. If you were to draw the Earth here, we know that even though we call this the North Pole, it's really the magnetic South Pole, and that's why a compass is North Pole will point towards what we call the North Pole because it's really the Earth's magnetic South Pole. But to answer this question, yes, the arrows, the field is going to go from north to south. I've drawn 2 magnets up here, and it says like magnetic poles repel, unlike magnetic poles attract. Well, that is true. All right, this goes from north to south, and what that does now is it's going to pull these together. So yes, like magnetic poles repel and unlike ones will attract each other. Okay, when a current carrying wire is placed in a magnetic field, a force exists on the wire perpendicular to both the field and the wire. I'm going to forget about what I have drawn here. Okay, this is when a current carrying wire is placed in a magnetic field, a force exists on the wire perpendicular to both the field and the wire. Well, that's true. In here, we've got the current going to the right, the magnetic field is going up. If you use your right hand and point your fingers in the direction of the current, so my fingers are going in that direction, and then loop them in the direction of the field, your thumb would have to be pointing at us. So that's why I've got the force now coming out. That little dot there is showing the force is coming right out of your screen that you're looking at. So that is true. Okay, now we're going to do a little bit of review here. It's going to be on your test, talking about electrical forces, because we're talking about magnetic forces, electrical forces. A lot of it's going to be on there. When we're dealing with these electrical forces, what I want you to understand is, remember, is if we have two positive charges, all right, well, what are they going to do? They're going to repel each other. If we have two negative charges, they're going to repel each other. How about if I have a positive and a negative charge? Well, those two are going to be attracted to each other. So the one that relates this the best would be C. Electrical forces cause objects to repel and attract each other. Okay, the distance between two charges, QA and QB, is R. The force between them is F. What is the force between them if the distance between them is doubled? Well, this goes back to that inverse square law that we've talked about several times. And what that is then is that the force is equal to Q, it's K times Q1, Q2, or A and B all over R squared. Well, we're not talking about changing the stuff up on top. So let's just say the stuff on top, let's just give it a number. So the force is equal to 100. We're going to say the top number comes out to be 100. And let's say in the first case that R equals 1. Well, it would be 1 squared, or 100 newtons would be the force. It says, what if the force between them is doubled? So now let's say, what if R is 2? Well, the force on top, the number on top is still going to be 100 because all we're changing is R. But if it's no longer 1 squared, it's 2 squared, or it's 4. So 100 divided by 4 is 25 newtons. So what happens? Well, the force is 1/4 of what it used to be. Okay, which of the following is true about the direction of an electric field? Well, what we said is an electric field would be heading in the direction we've got positive and a negative charge. Which way is an electric field going to go? Well, we said that imagine you had this small positive test charge. Which way would it go if it was put between these two charges? Well, it would be repelled by the positive and attracted to the negative. So what that tells us then is the electric field goes in the direction from a positive charge to a negative charge. Okay, positively charged particles in an electric or magnetic field. Well, think about an electric field. And we just said that a positive charge would go to the right in this case. How about if we put a negative charge in there? What would it do? Well, it wouldn't go to the right. It would be repelled by the negative charge, and it would go in the opposite direction. Well, we learned that charges behave the same way in magnetic fields, meaning they head in opposite directions. All right? An electron is going to go in the opposite way as a proton. A proton is going to head in the opposite direction as a electron, whether it is in an electric field or in a magnetic field. Okay, what this problem is saying here is the work, which is the potential energy. All right, it's going to be doubled, so it's going to go from 10 to 20. Remember, potential energy in work is energy, so we can say it's the same. The strength of the charge is halved, so it goes from 1,000 coulombs, let's say, to 500 coulombs. Well, what's going to happen to our answer? Well, it goes from 100, all right, And here it's going to go up. It's going to be much smaller. All right, it's going to actually be 25. So what happens? It's going to decrease to 1/4 of its original value. What I want you to remember here is draw numbers, put numbers in. We've had a couple problems like this. Put numbers in representing what they were, and then change the numbers according to what it says happens to those different parts of the equation. Hey, that's everything for today. We only got to question 13, but I'll see you tomorrow on the flip side.